Hello. Okay, so welcome back to day 4 of this GIAN course on role of reliability. So we have Professor Lalit Goyal sir with us. So he'll continue with the session. I welcome sir to continue the further knowledge to be shared.
थोड़ा चल रहा है, थोड़ा नहीं चल रहा। एक ही बैटरी लगती है क्या? Okay, good morning, ladies and gentlemen. Looks like we are losing a lot of people. They have given up on me. That's the only way to look at it. Okay, maybe should we wait for a couple more minutes, or do you want to penalize them because they are coming late? Okay, so then I can wait. Who is Shama? Shama? There's someone called Shama? Shama? Connected with me on LinkedIn yesterday. Nobody by that name? But she's from DTU, so I thought maybe she was here. और आ रहे हैं? We can start, sure? Yes. So we penalize the others. Okay, all right, good morning again, ladies and gentlemen. So yesterday we were talking about generating capacity reliability evaluation. We started to talk about the generation model in the form of a capacity outage probability table. It's a simple table showing the capacity states and their corresponding probabilities. So it's as simple as that. We also said that instead of using state probabilities, we can use cumulative probabilities, and that is sometimes advantageous because we can directly find the cumulative probability of X or more megawatt out of service by just looking at one value rather than adding up a few values. Yeah. So we spoke about that, we looked at a few examples, and there were some exercises for your doing pleasure and hopefully you are up to speed with respect to what we have done. So we talked about binomial distribution first, and then we said, okay, maybe the the components or the generating units are not identical, then you can't use binomials. So I gave you an example of that as well. And then we said that, okay, generators need not exist in two states all the time. So how do we model three-state units? So that's the one that we want to talk about today. Before we look at the calculation of the risk. Remember when we started with the generating capacity reliability evaluation, we said that we need the capacity model, we need the load model, and then we are going to convolve the two to get the risk model. So we are going to approach in that direction after completing this last aspect from this particular chapter, chapter number 6. Okay? Any questions so far? I usually ask for questions, comments, brickbats, as well as bouquets. You can throw anything at me. Okay? So multi-state unit representation. You look at that equation, the cumulative probability, uppercase P is cumulative, remember? Lowercase p is state probability. So uppercase P of the capacity outage state X, which may be 0 megawatt, 20 megawatt, 40 megawatt, whatever, is given by summation of the probability multiplied by P prime of X minus Ci. So there is a Pi and there is a Ci, and I is going from 1 to n. Now suppose we go back to the two-state unit for argument's sake, then it will be I equal to 1 to 2, correct? And then we'll have P1, P prime X minus C1 plus P2, P prime X minus C2, am I right? Imagine that the generator exists in two states, 0 megawatt out and 20 megawatt out. And the probability of 0 megawatt out is 0.99 and the probability of 20 megawatt out is 0.01. Availability and unavailability, correct? So what will this equation boil down to? 0.99 multiplied by P prime of X minus 0 plus 0.01 P prime of X minus 20, correct? Is it not the same as what we have learnt yesterday? So this equation actually reduces to what we have seen yesterday for a two-state unit. So now we are generalizing it. You can have any number of states of a particular generator. It could go from 1 to n. But typically we use, as I have been saying, 3 states at most, yeah, typically. Doesn't mean that you can't include more. As long as you have the data, why not? The basic problem is that we don't have the data. And then you don't have the data, you just pick some numbers from thin air, you are going to get thin air. Garbage in will be garbage out, right? As I said yesterday. So this is the equation that we need to now use, where Ci is the capacity outage state of unit that we are adding, right? So let's go back to this example 6.4, and I'm going to change the fourth unit. Yeah, the fourth generator. We are not going to change the first 3 generators, and that is advantageous to us. Why? Then I'm building the capacity table, right? I add 1 unit, then I add the second unit, then I add the third unit. So I don't have to change those 3 tables. That's the advantage. If I put this as the first unit, everything will change, even though the end result will be the same. So the loading order does not affect the COPT, capacity outage probability table, but the way we are building it, the answers, intermediate answers will be different, right? So in order to save us that time and effort, I'm not changing the first 3 generators from this example, but I'm changing the fourth generator, the 40 megawatt unit, and instead of the 40 megawatt generator being existing in 2 states, now I'm saying that it can exist in 3 states. So the state is I, the capacity outage is Ci, and the probability of that capacity outage is Pi. Clear? Those are the things that we will need for this equation. Yeah, the small Pi, state probability, the small Ci, capacity of that particular state being out. Okay. So since the first 3 units, the 20 megawatt units of that example are still the same, no change. So therefore steps 1, 2 and 3 will remain the same as before. It's only step 4 which will change. So what will step 4 look like? We now add the 4th unit. What values can X take? It's still the same, 0, 20, 40, 60 and 80, because even though this 4th generator can exist in 3 states, the values are all multiples of 20. So therefore it doesn't change anything. If I had said 0, 15, 40, then things will be different, right? So now it's 0, 20, 40. So everything is still a multiple of 20. So the first step will always give us 1. We spoke about this yesterday. Cumulative probability of 0 megawatt or more out of service will always be 1. You can test it out. Then cumulative probability of 20 is the probability of the first state. Here, go back again. Probability of the first state multiplied by p prime of x minus 0. Correct? Plus probability of the second state multiplied by p prime of x minus 20 plus 0.01 multiplied by p prime of x minus 40, right? So because I have to go back and forth in slides, so I'm just trying to put the things together, right? So that's what we have. 0.95 times p prime of x minus 0. The first one is x minus 0. What is the x that we are adding? Yeah, what is the x? We are adding 40 megawatt unit, correct? Correct? The unit capacity is 40. So 40 minus 0 is 40. So p prime of 40, we got to go back several steps later. Yeah, here. Step 3, p prime of 40. Is that the same question? Not sure. Yep, this is the question. I thought it was 6.4. Yeah, this one. Yeah, so from here, no. It's the previous one, this one, right? Yeah, so step 3. So p prime of 40 is 004672. Where am I now? Going back and forth. Sorry? No, here it is P20, right? Yeah, so x minus 20, so 40 minus 20 is 20, right? So that's correct. And then 0.04 times p prime of x minus, if you go back to this, x, yeah, this is 20, the second one. The first one is 0. Are we doing the right thing? I just want to make sure that the number is correct. Yeah, 0.115264. Step 3. P20, so P20 is pi, p prime of x minus ci, right? So x is 20, 20 minus 0 is 20, right? So 0.115 plus pi, p prime of x minus ci, 20 minus 20 is p prime of 0, which will be 1, plus 0.01 times p prime of x minus ci. Ci is 40, so 20 minus 40 is minus 20, and that probability will always be 1. Okay. Then 40 is 0.95 times p prime of x minus 40 minus 0, 40, so that's the number coming from step number 3, and this number is coming from step number 3, 40 minus 20, and this number will be 1. So like that, you see that we can still calculate the capacity outage probability table. So it doesn't matter, you can include 3 steps, 4 steps, 5 steps, but the basic equation is the same, except that now we can generalize it in this particular form. Yeah. So it is actually the same equation that we used for a 2-state model as well. Okay. There is an exercise for your doing pleasure, as always. Have you been doing these exercises in the afternoons or elsewhere? You have? Okay. You have been practicing? Okay, very good. There is a test tomorrow, remember? Yes. Half an hour test. Oh, okay, so we need to change the chapter. Chapter 7, please, CH7. Okay. So now we know how to model our generation capacity. Okay. I hope that you are all experts in calculating the capacity outage probability table. We learned the recursive algorithm. We know how to deal with binomial distribution, right? So as long as components are identical, you can use binomial to get the COPT, but usually they are not. Especially in a large parse system, they will not be. So therefore, you must use the recursive algorithm. Now, we have two types of reliability evaluation techniques, analytical techniques and simulation techniques. Again, what are we after now? We are wanting to go towards finding the risk in the system. How do we define the risk? How do we quantify the risk? It is in the form of loss of load expectation, loss of load probability, loss of energy expectation, and things like that. I gave you a list of 7 or 8 reliability indices. You can find any of them. Yeah.
In the previous question, by using the cumulative probability, how can we draw the conclusion? Just referring the previous example where we were having 320 megawatt generator and 140 megawatt.
Correct.
We draw the chart of the cumulative probability.
Yeah.
Now, what conclusions can we draw from?
Yeah, so from that table itself, you cannot draw any conclusion because the conclusions are drawn from the risk rather than from the capacity model. So you will be able to see.
In conjunction with some other model also.
Sorry?
That cumulative probability shall be used with some other tools also to draw any conclusion.
Yep, that's where we are headed now. Yeah, thanks. So there are two types of calculation techniques to calculate the risk. That's what I'm saying now. One of them is called the analytical techniques, which is what we are focusing on, and the other is called as simulation techniques. The analytical techniques evaluate the reliability indices using mathematical models. And of course, we know by now that we make many approximations, many assumptions when we derive these mathematical models. So the answer is also not very accurate, but still we believe that it is the best way to do it rather than to make the model so complex that even the result may not be any more meaningful. The other method is called the simulation technique, and usually we use Monte Carlo simulation. Some of you might have used it in your own research. It's a very elegant tool, and more often than not, the way it started in reliability evaluation, it was used more in Europe, whereas in North America, more analytical techniques were used during the time that I was a student. Of course, now things have changed. Now the computing power has increased tremendously. So therefore, both the techniques are equally popular everywhere. But there are problems with both the techniques. As I said, for analytical techniques, you can only calculate the expected values. You don't know the probability distribution of those numbers. Like LOLE, we are going to find the LOLE. But is it described exponentially? Is it described Weibull in a Weibull, Rayleigh, or normal way? We don't know. That's not what the analytical technique tells us. Whereas the advantage of the Monte Carlo simulation is that it will give you the probability distribution as well. However, there are also disadvantages there, because depending upon the technique, and there are two types of simulation techniques, non-sequential and sequential. Non-sequential considers each time interval independently. So that's why it's called non-sequential. There's no sequence. You take every time interval as it is. Whereas in the sequential approach, you take each time interval in a chronological order. Both the techniques exist. Depending upon the application, one type is more powerful than the other. But it has also got some problems, because if you observe this paragraph, says one problem inherent in all simulation techniques is that a specific solution is not arrived at. The solution is dependent on the number of experiments, the number of simulations. You call it experiments, and usually sometimes you have to run the simulation for 100,000 times. Some of them, simpler ones, maybe 10,000 times, but the larger the number here, the greater the accuracy in the end result. It is also dependent upon the starting value or the seed value that you use in the simulation and the sequence of random numbers generated. So random number generator also becomes important, right? So we can't keep saying, oh, there are limitations there, there are limitations there, then what the hell can we do? We can't use anything, right? So we might as well use something that gives us a reasonable answer, especially when we are doing long-term planning. Anyway, there will be so much uncertainty in it. Maybe you got to revisit that every 2-3 years to modify your plan. Yeah, make sure that you are going with the times. Yeah. So there are these two types of techniques. I just want to tell you that there are these two types, but our focus today in this course is on analytical methods. Okay. Simulation methods, you will definitely need computers. There's no way I can teach you just like this using simple examples. So we are now moving towards the loss of load expectation evaluation using the analytical technique. So in order to do that, I will need the second model, which is the load model, right? We have talked about the generation model, but we haven't talked about the load model. So let's look at the load model. There are two models that are commonly used. Both are sort of related, but one of them deals with the daily peak load. One of them deals with the daily peak load. So, you know, Monday, the peak load is this much. Tuesday, the peak load is this much. You don't consider the load hour by hour. You take just the maximum load on a particular day, and we use that. And then we arrange them in a chronological order, in a descending order, and then that curve is called the daily peak load variation curve. The other curve is the load duration curve. Load duration curve takes the hourly loads and then arranges them in a descending order. So one deals with hourly loads, the other deals with daily loads, right? But if you look at the load duration curve, because it deals with hourly loads, the area under this curve is actually the energy required by the load, because it deals with hourly, megawatt hours, kilowatt hours, gigawatt hours, you will get directly. Whereas if you use the daily peak load curve, it's not going to give you exactly the energy. Yeah, it's the load is in on a daily basis, so it gives you in days, megawatt days, gigawatt days, not in megawatt hours, right? So that's not a true representation of the energy required by the load. So that's why whenever energy calculations are needed, we use the load duration curve. But if you are only after the loss of load expectation, you could use either. And I'll show you the use of both of them, hopefully. One through an exercise and the other through an example, okay? So the typical shapes of these two curves are shown here. The daily peak load variation curve, the load duration curve, and this is the time in per unit. It could be like over a month, it could be over 6 months, it could be over 1 year. So if it is 1 year, then this one represents 8,670 hours or 365 days. So for the daily peak load variation curve, it could be 365 days, yeah? Or for the load duration curve, it could be, if you are doing it for the whole year, it could be 8760 hours. If you are doing it for a month, it is 720 hours, okay? 24 times 30. So in the analytical approach, we use the COPT and we combine it with the load characteristic to get the risk. Yeah, as simple as that. So you will see through calculations, it's not that hard at all. But before we use the COPT, you must realize that there is a difference between the terms capacity outage and loss of load. Yesterday I told you that when we develop the capacity outage probability table, we should know what is loss of load, correct? That means whenever the capacity becomes less than the load, after you have considered all kinds of remedial actions, support from interconnections, voltage reductions, voluntary load curtailment, and so on and so forth. And still, if your capacity is less than the load, then you will curtail load, you will cut load. So that situation is loss of load. But capacity on outage may not result in a loss of load, right? Suppose my installed capacity is 10,000 megawatt and my peak load is 7,000, and one of my generators, 1,000 megawatt, goes out. I still have 9,000 megawatt. Therefore, there is no loss of load. So we must make sure that we understand these two terms correctly. So the term capacity outage indicates loss of generation which may or may not result in a loss of load. Yeah, it could, it may not, okay? So loss of load only occurs when the generating capacity is less than the load. So now let's try and understand this from this particular figure. From this figure, you notice that this is the daily peak load variation curve over 365 days, for example. And this is the installed capacity in megawatt. This is the reserve in the system, because anything greater than the peak load is obviously the reserve in the system. And suppose there is an outage O subscript K. O stands for capacity outage, outage. And K means it could be outage 1, outage 2, outage 3, where K goes from 1 to whatever. How many states are there in the capacity model? That's what K goes from, yeah? So suppose there is this outage O subscript K which happens to fall here. Obviously, we are not able to meet the entire load, are we? We are not able to meet the entire load, isn't it? Because the peak load is here and my capacity outage is this much, so I only have this much capacity, correct? I only have this much capacity. So how many time units I am not able to supply the load? I repeat, how many time units out of 365 days I am not able to supply the load? We need to calculate this using the daily peak load variation curve or the data which you have arranged chronologically or in a descending order. So when you have got a computer program, that can be done very easily. For us, because we can't use computer programs here, so I'm going to assume in an example very soon that this is a straight line. That makes my job easier, your job easier, right? Because everybody can then write the equation of the straight line and then we can find these time units very easily. Right now you can't. When it is a curve, then you can't, right? You need all the data, every day's data. Whereas when it is a straight line, we don't need that, okay? So this is how we will find for each OK, we will find TK. Then we will go to the next outage, we will find the next time. Next outage, we will find the next time. And how do we find the LOLE? What is LOLE? Loss of load expectation. Remember the key word, expectation. On the first day, I told you that expectation is nothing but the mean, correct? Basically, the word expectation is the same as the mean. So, in other words, if I have so many scenarios, O1, O2, O3, O4, T1, T2, T3, T4, if I do an expectation, what will I get? I will get the probability of this times the time units. So, I'll have P1, P2 plus P2, T2 plus P3, T3, etc. And that will give me the risk in the system. So the loss of load expectation is nothing but Pk, Tk time units, where K goes from 1 to N. Very straightforward. You know the probability of each outage, don't you? From the capacity outage table, you already know Pk. You need to find Tk, yeah, using this sort of a notation. So whenever there is an outage, you find the time units that we are not able to supply the load, either using a software or using the equation of the straight line, or any other format in which the load curve is given to you, okay? It's not an instant, it's a period. It's a period, yeah, it's not an instant. See, we are not able to supply the load for this period, isn't it? Yeah. So it's a period, it's not an instant, correct? So this is the equation for LOLE, summation Pk Tk. We can also use the cumulative probabilities. It's a question that you have been asking, how do we get this into play? We can use the cumulative probabilities, then the LOLE will be capital P uppercase Pk times Tk minus 1. So then you have to find the difference of the time units because you are using cumulative probability. Yeah. So if I go back to this one, suppose this is T1 and then we'll have a T2 here. So if we use cumulative probability, it will be T2 minus T1. It will be the difference of the time units. Yeah. We'll see the example and then I'm sure you will understand it better. So if the load characteristic is the load duration curve, the units for LOLE will be in hours per period. If the period is a year, hours per year. If the period is a month, hours per month, yeah, and so on. And for a daily peak load variation curve, it will be in days per period, obviously, correct? And the period of study could be a week, a month, or a year. And we could even include generator maintenance and generators being decommissioned, new generators being added. We can include all of that in a more detailed study. Okay. So let's look at an example. Nothing better to understand than by use of an example. The application of equation 7.1 and 2 can be illustrated using this example. 5 40 megawatt units, each with a forced outage rate of 1%. So you can use the binomial distribution to calculate the capacity outage probability table, right? So that's what I have done. Further, I have stopped here. Why did I stop here? Because actually this should go up to what? 40 times 5 is 200. Actually it should go next 160, then 200, right? And the probabilities will be very, very small. So I am ignoring or neglecting all the probabilities below a certain value, that is below maybe 10 to the power minus 6, if I'm not wrong. I must have mentioned somewhere, below 10 to the power minus 6 have been neglected. If you don't want to neglect, be my guest. These days calculators have up to 14, 15, 16 decimal places, so go on, do it. The result will be different in the 8th or 10th or 11th decimal place. Big deal. Yeah. So really, we don't have to be so specific, right? Just stop at 10 to the power minus 6 or minus 8, whatever you feel comfortable with. Okay, so our daily peak load variation curve is given by this straight line between the 100% peak load percent. So this is given in percentage, and the 40% peak load. Yeah. So what does the 100% represent here? Yeah, the peak load is 160 megawatt. So this is 160 megawatt, and this is 40% of 160, so 64 megawatt. Okay, you can do it in megawatt, you can do it in percentage. It's up to you. I think everybody knows how to write the equation of a straight line, so I'm not going to dwell on that. Okay, y is equal to mx plus c, where m is the slope, and the slope is y2 minus y1 over x2 minus x1. So you can actually easily calculate the slope. Okay, and then calculate for any value of y, you can calculate the x. That's what we are after, right? Remember I told you I want T1, I want T2, I want T3. What are those values? T1, T2, T3, they are x. Y is equal to mx plus c, they are x, right? And of course y is the corresponding value here, corresponding value here, corresponding value here. The slope is easily determined, okay? So we use 7.1 or 7.2. You can use both individual and cumulative probabilities. So I just want to illustrate using this graph again how the calculations are done. So our installed capacity is 200 megawatt. Our peak load is 160 megawatt, correct? Right? Installed capacity is 200, 5 generators of 40 megawatt each, and the peak load is given as 160 megawatt. So if none of the generators is out, we have 200 megawatt, we are able to meet the load, right? So there is no loss of load, correct? That equation, if I use that equation pk, tk, yeah, the time unit is 0, right? So that first thing, when there is no outage, no generator is out, that is pk, tk is 0, right? Then the next one, the next outage is 40 megawatt, right? How many states are there? We just use this table, right? 0, 40, 80, 120. We are stopping at 120, right? So to make things easier. So 40 megawatt out, I know the probability. I also know the cumulative probability, but I'll come to cumulative later. For now, I'm just using the state probability. So I know the probability. What do I need? I need T2. I need the time units corresponding to 40 megawatt out. But I look at this, 40 megawatt out means I'm still able to meet 160 megawatt, correct? So therefore, I'm not losing the load at all. Yeah. So that number will also be 0. That number will also be 0. The time units 0, 0. Can you see that? Tk for the first outage, meaning no generators out, is 0. Tk for the second case, one generator out, 40 megawatt, is still 0, because we are not losing load. There is no loss of load. Clear? Then the third case, when 2 generators are out, we lose 80 megawatt. Then of course 80 megawatt is here, and this is my load curve, and I'm not able to supply the load for this time T3, small T3, okay? I'm not able to supply the load for this small time T3. So you can calculate this time using y is equal to mx plus c, yeah? And you will find that it is 41.7% in terms of percentage. Okay, so then the next outage will be 120 megawatt, and then you can find this T4, small T4, yeah? Again, using the equation of the line. So actually we have all the T's and we have all the P's, and all we need to do is now P times T and PK, TK, and then add them all up and you'll get the risk in the system. Okay. Now I mentioned about the cumulative probability, so I think we can use the same figure to even look at cumulative probability. So what happens when the outage is 80 megawatt? We are going to use uppercase T3, which is small t3 minus T2, but there is no T2, T2 is 0. Therefore, outage, it will be 41.7 minus 0, so it will still be 41.7. But for the 120 megawatt out, we have the small t4 and small t3. Therefore, the difference of the two is t4 minus t3, which is uppercase T4, which also happens to be 41.7%. So that's how we will do the cumulative probability table and calculate the risk. So this is the calculation of the risk. We know the individual probability, we know the TK, so we can calculate LOLE, which is PK, TK, and this is what we get, but this is all in percentage. So we need to eventually multiply it by 365 days, yeah? And because it is percentage, we need to divide by 100. So you will get 0.15 days per year, because the period was supposed to be 1 year, 365 days, so it is 0.15 days per year. Remember that reference that I have been talking about, 0.1 days per year, so this is 0.15, pretty good, yeah? If the cumulative probability values are used, then this is what the table will look like. We know the cumulative probabilities, yeah, I know by now you all know from the state probabilities how to determine the cumulative probabilities, and then the uppercase T, so this is cumulative probability, uppercase P, uppercase T, for the first two cases 0, third case it's the small t3 minus 0, and for the fourth case it's small t4 minus small t3, which also happens to be 41.7. Do the same thing, PK, TK, and you will get this multiplied by 365 over 100. It's the same result. The loss of load expectation is unique, okay, 0.15. Very soon we will see what happens to this value when we include uncertainty. We have been talking about the uncertainty, and we also spoke about the probability distributions on day 2. And one of the probability distributions we learned was the Gaussian or normal distribution. So we'll see an application of the normal distribution today, okay? Any questions about the LOLE calculation? This is the risk in the system, okay? So if you want to use the cumulative probability, and if the load, now I am assuming now a very pessimistic situation. Now let's go back to what is our goal. Our goal is to do long-term planning, yeah? Long-term planning, adequacy. Remember adequacy and security? I'm after adequacy, not security. Adequacy means existence of sufficient facilities of generation, transmission, distribution to meet the load demands at some time in the future. So you are doing future planning, right? So when you are looking at the future planning and you say that the load is like this straight line, somebody can argue, why are you trying to make things so complex? Why not assume the load to be constant? I'm 15 years away from today. Can I say that the load will be like this? Yeah, why not just take a constant value? Take different constant values, find out the implications, and then decide, you know, where you want to stay, how much you want to reinforce the system. That's one way of doing it, yeah. So if the load is assumed to be constant throughout the time period considered, that means 160 megawatt, not like this, but like this, right? 160 megawatt. So if that is the case, then we can use the cumulative probability of the first negative margin, first load loss state, to get the LOLE. That's the advantage of the cumulative probability capacity table, which I also mentioned yesterday. So if you look at the cumulative probability table, assuming the load to be constant at 160 megawatt, so when we have 40 megawatt out, we are still okay, correct? When we have 40 megawatt out, we are still okay, no loss of load. When we have 80 megawatt or more out, then the cumulative probability is 0.000980, correct? So If the load is constant at 160 megawatt, my loss of load expectation is 0.000980, of course as a percentage. So you need to multiply it by 365 and this is what you get. So the risk in this system is 0.35 versus 0.15, more than double. But when you are comparing alternative options, the numbers don't mean much, right? Because you are going to compare the alternatives and see which one is probably best for your own system. But we have at least an analytical method to calculate and to give us the quantitative reliability indices for which we can base our judgment, right? Eventually, of course, you still have to use your judgment, but at least you have the basis for that judgment, okay? So that's what we have done now. We can use any of the load curves, but constant load gives you a pessimistic appraisal. Pessimistic, obviously, you can see the number is much higher, yeah? 0.35, which is almost more than double of the number that we obtained using a load curve, straight line curve. So while the load is not expected to remain constant, for planning purposes, a single load level may be adequate, especially when you are comparing alternative strategies, alternative options. That's all I'm saying. So you have the option. You want to consider the load curve, which is so uncertain in the future, you can do it. Alternatively, just use a constant load level. You get an idea of what kind of risk will exist in the system. It may be a pessimistic appraisal, but isn't pessimistic better than optimistic? Because the load is likely to be much more than what you are expecting it to be, isn't it? So we are better off with a pessimistic appraisal in many ways. So there is an exercise for your doing pleasure, as always. So I have given you the hourly load data for 24 hours. Yeah, it's actually very simple. And I have even drawn for you the load curve, the load duration curve over a 24-hour period. And I am asking you to calculate the LOLE. Let's read the question. 425 megawatt, 1% forced outage rate unit with the load data given in table 7.4. The load duration curve is given in this figure. The objective is to determine the risk. Okay. So what is the total capacity? 100 megawatt. Yeah, you can find the capacity outage probability table using binomial. Yeah, and then you can combine it with this load. You see the loads here. I didn't draw the curve for you initially, but later I said, okay, let's make your life simpler, nicer. So you see the maximum load here. You just look 74. Yeah, maximum load is 74, right? Is it? Am I missing something? Oh, yes, 82, yeah. I'm not getting any younger. So 82 is the highest load and 32 is the lowest. So here it is, 82, you're right. 82 all the way up to something like 32 or 34, whatever it is. So hourly, right? It's changing hourly, correct? So it's not like a straight line. You can approximate it using, your least error squares algorithm and things like that by a straight line if you want. But it's 24 hours. It's not 8760 hours. So it's very doable by hand calculations. Yeah. And if your load is 82 and the installed capacity is 100, so you are somewhere here, right? So if one generator goes out, 25 megawatt, you only have 75. You're going to lose load, correct? So how many hours are you going to lose load? You can just go here, you'll find it is 1 hour or 2 hours. And then you do LOLE is equal to PK, TK. That's it, very simple. I've given you the answer. It shouldn't be a problem, 0.049 hours per day. Because the data is for 1 day. So it will be hours per day. I remind you again, this is a time unit, this is a time unit. You can actually convert the hours to days. So it will be days per day. And then what will you get? Loss of load probability, LOLP, right? The two are related. However, this is more meaningful. You and I can relate to it, right? How many hours am I not going to get supplied today? 0.049 hours, right? Whereas if I say the probability of not being able to fulfill the load today is 0.98, that is not so meaningful, right? So the two are related and yet this is more significant. Okay, now we have shown some studies. We know now how to calculate the risk in the system. Let me show you what happens when we change some of the parameters. Because when you do long-term planning, you don't know the forced outage rate of generators. Yeah, you probably can only think of the capacities of the generators. Even those may be derated, like a 40 megawatt generator 10 years down the road. Maybe it will not produce 40. Maybe at most it will produce 35, 36, 37 megawatt. So how do you include all those parameters in your calculations? So I'm going to show you some of them. Changes in peak load, changes in the unavailabilities of the generators. How do they impact the risk in the system? That is what we call sensitivity studies. That's the advantage of any research. Once you have the algorithm, once you have the program or whatever you are using, you just vary the parameters and see how it impacts the output. So that's what I'm going to share with you. So the system risk for a given capacity composition is dependent upon the unavailability values of the generators. How? We'll see shortly. Alternatively, I can also argue that the risk is dependent on the peak load, isn't it? Just now in the example, we saw that the peak load was 160 and the installed capacity was 200, right? So if I change the peak load, do you think that the risk will remain the same? Generally, you would expect that if the peak load increases, the risk will also increase. And if the peak load reduces, the risk will also reduce. So you have a way to quantify those things through these techniques. Intuitively, we know which way it's going to go, but how much, we don't know, right? We can only use these algorithms. So let's go back to this system with 540 megawatt units, 1% forced outage rate, and we change the peak load. Yeah, so we change the peak load, and you see 160 megawatt peak load, this was our risk, remember? From the previous example, we found the risk to be 0.15. Now I change the peak load 200, the risk becomes 6 days per year. And if I reduce the peak load to 100, it's only 0.001 days per year. So you can see the variation. Now we can quantify the risk. Are you, as a management or as a manager or the boss of the company, of the organization, are you willing to accept that this will be the peak load and this will be the risk? Or you think that the peak load will become higher and therefore the risk will be this, and therefore you want to mitigate the consequences of that risk level. So that is where the engineering judgment will come in, of the planners, operators, managers, and so on. So this forms a very good basis when we do sensitivity study. So this is with the peak load. We can do another sensitivity. So this is just showing you in a graphical way, the loss of load expectation here versus the peak load. So you can see 160 is where we were, 0.15, the risk was 0.15, yeah. So as the peak load increases, the risk becomes higher. It goes up to 6 days per year, remember, from that table. Now we change the forced outage rate of the generators. We change the unavailability of the generators, because that's also not known to us. In the years to come, we expect that, okay, the manufacturer is telling us based on past data that the forced outage rate of this generator will be 1%. But we know that it is uncertain. So we can also include that uncertainty, change the forced outage rate. When it was 1%, our risk was 0.15. If it goes up to 5%, the risk will be 3.6 days per year. So we can quantify everything. Where do you want to draw the line? It's entirely up to you. If you think that it will drop to such an extent, then you need to be prepared for this risk in your system. Are you going to do anything about it by adding more generators, yeah, or reinforcing the system in other ways, or not? Maybe you want to allow the system to degrade, yeah, because there is still uncertainty. Maybe it's not going to go to 5%. Maybe it'll only go down to 2%. So you have to decide. That managerial decision is still in the hands of people. We can't let the computers decide that for us, okay? So we can see that based on these two parameters, the peak load and the unavailabilities of generators, how the risk profile can change. And this is an excellent tool in our hands to be able to predict the performance of a future electric power system, generating system. We are still on generation, remember. We have assumed the transmission and distribution to be fully reliable and capable of transporting the generated energy to the load points, to the consumers, correct? I also show you a very large system result which of course you can only simulate using a computer. So this system has a capacity of 10,100 megawatt. What's the capacity of the system that we studied here? 100 megawatt, right? Or 200 megawatt, sorry, 200 megawatt, 10,100 megawatt, right? This is a large system, fairly large system, and it has some 300 and 500 megawatt units. So you see what we did? We changed the forced outage rate of these 300 and 500 megawatt units from 4% to 13%. And you can see the impact on the risk, yeah? And as you see, the profile is smooth. If you go back to this one, the profile is not smooth, yeah? So when you have a small system, the perturbations in the risk are significant. But you have a much larger system, the perturbations will usually be smoother. But you add a very large generator, if you add 1,000 megawatt generator, then this risk profile will not be so smooth. So all these factors need to be taken into account, but at least we have the tools, we have the resources to be able to come to a quantitative figure which we can use to justify any reinforcements. Okay? Now, scheduled maintenance, we haven't spoken about that. What happens now? We are using a COPT and we are saying this COPT is valid for the entire year or the entire month or the entire day. But what happens if one of the generators is on maintenance? Then either the load needs to be changed or the generating schedule needs to be changed, right? So maintenance can also be incorporated in our generating capacity reliability evaluation. It's not that straightforward, but it can be incorporated. So this is one way of finding the risk in the system by considering the maintenance schedules. So I'm going to show you this one first. So this is my load profile. This is my load profile. This is the reserve in the system, and this is the total installed capacity. And let's say that these are the units on maintenance. Yeah. At different times, of course. You don't maintain so many generators at the same time. You can see that from this period to this period, these generators are on maintenance. Then this period, more are on maintenance. Why? Because this is a winter peaking system, isn't it? This is January, this is December. So where is the peak? The peak is in December and January, right? So it's a winter peaking system. That means you will tend to maintain the generators during the low load periods. And that's exactly what you're doing. Most of the maintenance is during the low load, not during the high load, right? That can be catastrophic. You wouldn't want to do that, okay? So when we consider all these maintenance schedules, then we can use this particular equation, the loss of load expectation, the risk, yeah, the risk LOLEA can be obtained by calculating the risk over these small little periods. So you'll have to do several calculations. One generator or two are maintained on are under maintenance, then you use the COPT during that period, and then you convolve it with the load during that period. You will get one LOLE, right? So you'll get LOLE1. Then you do the same for another maintenance period and another maintenance period, and you sum them all up. You will get the overall risk in the system by considering maintenance schedule. So that's one way. The approximate way is this. The approximate way is this. Let's go here first. So approximate method of including maintenance is whenever some generator is on maintenance, I assume that the load profile is now going up by the capacity of the generator on maintenance. So for example, the generator on maintenance is 40 megawatt. The original load profile is the dotted line. Now I'm going to add 40 megawatts to the load profile, and I'm going to shift the load profile completely by 40 megawatt. Why? It is equivalent to the load going up by 40 megawatt, is it not? I have less 40 megawatt generation. Is it not equivalent to the load going up by 40 megawatt? I suppose it is. So that is one way of treating maintenance. You change the load profile, don't change the capacity outage probability table, and you get your risk index. That's one way. The other way is you have the installed capacity, and then you know the capacity on maintenance, so you reduce your capacity, total installed capacity, to a new level. So your reserve in the system is much less now. So that's another way of treating this calculation using maintenance. So there's various methods available in the literature, and the treatment of maintenance is not easy in terms of hand calculations. That's why I have not provided an example here, just the conceptual way of how you will introduce maintenance, okay? Now, one more thing that we need to introduce is uncertainty in the load. We have so far been using, okay, 200 megawatt installed capacity, 160 megawatt peak load, right? But the peak load is not so certain. So how do you include the uncertainty in the load? We call it load forecast uncertainty, yeah? LFU, I'm going to use that acronym, load forecast uncertainty. So we know that some uncertainty exists in the load, which is described by a probability distribution, okay? Now research needs to be done. We need to know how the load is distributed in the future or in the past. So there is not too much data available, unfortunately, but the available data suggests that you can use Poisson distribution. I must have written somewhere, maybe on the next. Yeah, here. Published data has suggested that the uncertainty can be reasonably described by a Gaussian distribution. Of course, not everybody keeps data of the loads, and therefore uncertainties cannot be modeled very easily. So what we do now is we are going to compute the risk for each load represented by the class interval. So in other words, remember the normal distribution, there were plus 3 standard deviations, minus 3 standard deviations from the mean, right? So we are going to assume that the load that we are predicting is the mean, and then we are going to go minus 3 standard deviations, we are going to go plus 3 standard deviations. We are going to do the calculations 7 times. One at the mean, one at minus 1 SD, standard deviation, minus 2 SD, minus 3 SD, plus 1 SD, plus 2, plus 3. And if you recall the Gaussian curve that I showed you a couple days ago, we already know the area under those minus 1, minus 2, minus 3. Can you recall? And those areas actually represent the probabilities of the load being in that zone. So we already know that. Only thing we now need to know is what is the standard deviation. Again, we may or may not have the data, but the good thing is you can do some sensitivity study. You can assume standard deviation to be 1%, 2%, 3%, 4%, and see, which appears to be more realistic to you. So that's what we are going to study now. So this is the table from the normal distribution. The mean value has the area of 0.382, plus minus 1 standard deviation. Each one has a probability of 0.242, plus minus 2 standard deviations, the probability is 0.061, and plus minus 3 standard deviations is 0.006. Let me show you this curve so that you can understand it better. So this is the Gaussian curve. If you are at the mean, this is the area under that, yeah, and the probability is 0.382. If you are at minus 1 standard deviation, 0.242, same as plus 1 standard deviation. So these are the probabilities, PIs, yeah. Now all we need to know is what is the time units that we need using that particular value. So using the mean, of course, we have already done the calculation, but we need to repeat the calculation 6 more times at minus 1, minus 2, minus 3, plus 1, plus 2, plus 3. So obviously this is more complex, it's more involved. So writing a small computer program will usually help. Yeah, and these days you have commercially available software for all of this. So I go back to an example to illustrate to you, which is always good for all of us to understand. Consider a generating system comprising of 12 5 megawatt 1% forced outage rate units. You notice that most of my examples I use identical units. Why? Because hand calculations are easier. You can use binomial. That's the reason. If I don't give you identical units, then you have to use the algorithm. Remember? Yeah. A times P prime X plus U times P prime X minus C. So it's a lot of steps, more work for you, whereas this is binomial, so kind of easy. Yeah. The forecast peak load is 50. What's the installed capacity? 12 times 5, 60. The peak load is 50 with the load forecast uncertainty assumed to be normally distributed using a 7-step approximation. Actually, you will be surprised to know that researchers have used 49-step approximation of the Gaussian curve, and they found that the results from a 49-step approximation is not too different from that of the 7-step approximation. Reason is simple. We are capturing almost 99.2% of the information within the plus minus 3 standard deviations. So are you really bothered about the remaining 0.8%? Yeah, and doing it 49 times? It's really not worth it, but somebody has done it. So now we know that we don't need to do it, right? So let's look at the remaining data. The standard deviation is given as 2% of the forecast peak. So forecast peak is 50 megawatt, so 2% of that is 1 megawatt, okay? So standard deviation is 1. The load duration curve is represented by a straight line at a load factor of 70%. For those who are not familiar with the term load factor, it is 2 times the minimum load is 2 times the load factor minus 1, so it's 0.4. In other words, it's going from 50 megawatt to 40% of 50, so 50 to 20 megawatt, okay, in a straight line. The loss of load, the risk is what we are after. So if you do the calculations, you will find that at the mean value, what is the mean value of the load? The mean value of the load is 50 megawatt. At the mean value, which you can calculate, right? You have your capacity outage table using the binomial distribution, and if the peak load is 50, use the cumulative probability of 10 megawatt or more out of service, and you can get the loss of load expectation, right? So I haven't shown you that table, but you can determine that, and you will find that that is 0.0252396 hours per month, because the data is given for a month. Now, this is the COPT, and again, I'm not including any stages after this because it's already 10 to the power minus 8 or something like that, right? So for the peak load to be 50 megawatt, these are the calculations. The risk is 0.025239. That's the risk. You can calculate using the cumulative probability table, okay? Now what I need to do is calculate the risk for 49 megawatt load, 48 megawatt, 47. Why? Because the standard deviation is 1 megawatt. So I'm going minus 3 standard deviations, I'm going plus 3 standard deviations. So I have to do the calculation 1, 2, 3, 4, 5, 6 more times. Until now I'm used to only one calculation, correct? Now I'm doing it 7 times total instead of 1 time. So you will find that the risk for each of these loads using the cumulative outage probability table, yeah, the COPT is 1 and only 1. That's not changing, fortunately. That's not changing. It's only the load that's changing. So you can get these numbers, and then if you weight the probability of each of these cases with the risk, then you will get the weighted value, yeah, expectation of an expectation, if you will. The risk itself is an expectation, right? So now I'm saying, oh, expected value multiplied by its probability of existence. So it's an expectation of an expectation. Yeah, so the weighted value turns out to be 0.78. Do you remember the risk in the system when we did not consider any uncertainty in the load? The risk in the system was this, 0.025, correct? Now the risk in the system is 0.078, 3 times, more than 3 times. So load forecast uncertainty must be considered. Here the standard deviation is 2%, maybe it's higher, and therefore this risk will also be correspondingly higher, right? So we have the tools, we know how to calculate them, we know how to include them in our analysis, yeah? So that's the question you were asking me the other day about uncertainty. So this is one way of modeling the uncertainty, okay? You want to take a break? Let me finish this 5 more minutes, is okay? I'm going to finish this chapter. I think it's coming to an end, if I'm not wrong. Exercise for your doing pleasure. And now the load uncertainty is modeled like this. So you don't have to model it by a normal distribution all the time. It can be discrete. Yeah, depends on your data, right? Yeah, if your load uncertainty, you think that it varies like this, whereas the mean is existing for 75% of the time, but it deviates by minus 10 megawatt 15% of the time, and it deviates by plus 10 megawatt 10% of the time. The good thing about this distribution is you need to do the calculation only 3 times. For Gaussian 7 times. So I'm making your life easier through this exercise, okay? And I'm also giving you the answer. So, madam, I'm making the life quite easy, right? Well, one more question which is similar, yeah, very similar, but we are using a daily peak load curve, a straight line between the 100% and the 40% points. Again, the answer is given to you, so you can try that. Just summing it up now, the applications of generating capacity reliability evaluation. So we have seen how to calculate the reliability indices. We have the capacity model, we have the load model, we convolve the two, we get the risk model. We also know how to do sensitivity studies. We can change the peak load, we can change the unavailability of the generators, we can include uncertainty, we can include maintenance. In fact, we can add generators, we can remove generators. I did not show you the recursive algorithm for removing generators, but it is actually the same equation, except that you rearrange it for unit removal. Okay, so there's many things that one can do. In a more detailed course, we can actually look at all that. But I want to share with you the on them by yourself relatively easily. At least that's what I hope. So the acceptable LOLE of 0.1 days per year has been used in many systems. If your calculated risk is worse than 0.1 days per year, it indicates the need to plan capacity additions. Or if you don't have the resources, you don't have the money to put more capacity additions, you might want to rely on purchases from neighboring systems. Maybe they're cheaper. That's why interconnected systems is so very important. We must rely on our neighbors and they on us so that we can share our capacity exchanges. And tomorrow, that will be the first topic tomorrow morning, interconnected power systems. Yeah, it's very interesting, very fascinating, obviously more complex as well, right? Or in the worst case, you still don't have neighbors that are willing to give you power, then what happens? Of course, the neighbors have the right? They can refuse. They want to feed their own first, not to feed their neighbors, right? So if that is the case, the worst case, you have to accept the temporary reduction in the risk. And you say, okay, at some time in the future, maybe I'm going to add capacity, but today I don't have the resources. So you just accept that reduced level of reliability. So we can choose appropriate reliability criterion, and if it is not a company, it's a pool of companies that they can also pool their resources. And the applications of quantitative reliability indices, there are many of them in generation capacity planning. And I've just listed a few here, which you can go through because you have the notes, especially to schedule unit maintenance. Because this is a very, very important field, asset management, as some of you have been saying. You want to maintain your assets, you must maintain them at appropriate times. When the system is experiencing the peak, you can't maintain, right? Even though your generators may be overloaded or maybe overheated or whatever, but you must try and get assistance and not maintain your generators, things like that. So it contributes to all kinds of things. You can calculate the reliability for a given expansion plan. You can decide what that expansion plan is, 5 megawatt hydro, 50 megawatt hydro, and things like that. And what is the reliability? You add generators, you know how to add generators, you know how to calculate the risk, yeah? You can do it for 10 years, 15 years, so everything is at your disposal. We can calculate the system reliability level for acceptability before retiring any old generating units. There comes a stage when you have to retire some generators. I mean, we also retire, right? I'm closer to retirement than you are. Yeah, you are much younger. The word retirement doesn't mean anything to you. Yeah, but everything must retire. So when you are about to retire an old unit, Hydro units, probably lifespan 50, 60 years, same for nuclear units, yeah. When you are about to retire and the load is going up and up and up, and you have not installed enough generation in the past few years, then you can delay the retirement, right? As long as you have the tools to find out how degraded your reliability will be. And evaluate economic trade-offs. I mentioned yesterday about the cost-benefit analysis. So that's something that you must also do year by year, if not earlier. And you can evaluate the effect of reliability of new technologies. These days, we don't have just hydro, we don't have just fossil fuel, we have all kinds of renewables. So you must also consider those, the impacts of those new technologies, management of load, and improvement of the availability of generators through maintenance. So remember always that we have assumed, we have made a lot of assumptions and limitations, and some of which are due to modeling difficulties and others due to data limitations. Please always remember that. What I'm teaching you is not something that is exact science. Yeah, we must, as engineers, we always have to make approximations and assumptions. Okay, so a few more assumptions that we have probably gone through earlier, but just to complete the story, the generation reliability evaluation assumes internal transmission adequacy. I told you that when we deal with generation capacity reliability evaluation, we assume the transmission and distribution to be perfectly reliable. Now that may be a valid assumption when you are starting to plan your generation, but as the generation comes into operation, things change and therefore you need to reevaluate your plans, right? So that's something that we must consider. Generating units are assumed to be running all the time unless they are on outage. May or may not be true. Yes, base load generators are almost always running, but not peak shaving units. Yeah. So therefore, we have to look at this in an operational manner also, which in this course we have not done. We have only looked at long-term planning, adequacy. That's why we call it adequacy. Finally, the loss of load condition defined in the planning studies may or may not result in actual load shedding. So we have been looking about capacity outage 0, 20, 40, 60, and we said, oh, loss of load, loss of load, loss. Maybe at that time there is no loss of load. Yeah. So there are so many uncertainties, and especially when we have the tools, we should be happy that we can model them at any point in time, right? And then the uncertainties in the estimates of the forced outage rates as well as the load demand would create an uncertainty in the calculated reliability indices. So please remember, the calculated reliability indices are long-term expected values. We don't even know their probability distribution. We just know the expectation, yeah, in the long term. So that's about it from me this morning, and then after the tea break, we have another chapter. Yeah. Thank you.
Thank you so much, sir, for informative slides and chapters on reliability. Now we can take a very short break. So arrangements of tea are in the senior machine lab, ground floor, electrical engineering department, and we can come back after 10 minutes.
Yeah, that 10 is usually half an hour, but that's okay.
Please be back after this consuming teas and all. We continue the session. Thank you. Ready to go? We have hands-on experience on MCs as well. Okay? Thank you so much.
See. Technology works in different ways.
Actually, the wire is touching that.
Okay. Is everybody here, or is everybody who's supposed to be here here? मैं पुश करूं? Okay, so I'll just close that door. So the next 1 hour or so, we are going to spend on looking at the calculation of the other risk index. We have been talking about the loss of load expectation all morning. Now we are going to shift our emphasis on the loss of energy expectation, yeah? Because we know that many systems are energy limited, especially with the advent of all these renewables, solar, solar, wind, geothermal, and all those. So they all have energy limitations. They don't have capacity limitations. So far we have been looking at capacity limitations more. In the future, we expect that there will be more focus on the loss of energy method rather than the loss of load method because of that. Okay. So calculations, we need to look at the load duration curve. Why? I mentioned earlier that the load duration curve is an hourly curve. Therefore, the area under that curve is actually the energy demand of the system. So that's what we need, right? If we know how much energy is required in the system, our objective now is to find out how much energy we are not able to supply due to those situations when there is loss of load. Okay? So it's just an extension of the loss of load expectation method to calculate the energy not supplied. We can also calculate some of the other indices that I mentioned perhaps yesterday or the day before, the energy index of unreliability as well as the energy index of reliability. Now the reason why we calculate these indices is that we want to compare two totally different systems on the same pedestal. That means they may have similar peak loads, they may have similar generation composition, but once you want to compare different configurations for the future, it is always better to compare them on a per unit basis. So that's the reason for the EIU and EIR, energy index of unreliability and reliability, to be used sometimes. I also mentioned another index again yesterday, if I'm not wrong, system minutes, SM. You remember SM? And the often quoted number is 25 system minutes, which actually means that for 25 minutes, the energy will be lost at the time when there is peak load. That's the actual meaning, yeah? But usually that number is much higher. You saw one example today in the morning, and again we'll see an example. We'll see system minutes is much higher than 25. So we go back to the curves that we saw in the morning. Remember the O subscript K? Yeah, we are going to use the same notation. What is O outage? Outage, O1, O2, O3, and then small p, P1, P2, P3. And now we are adding another index, another number. It is called E subscript K. So E is the energy curtailed by a capacity outage, OK. Energy curtailed, not energy supplied. Energy curtailed, not supplied, okay? So that's what we will see when we look at the graph. And how we'll calculate the LOEE is very similar to how we calculated the loss of load expectation. Instead of PKTK, we've got PKEK, right? Because this one deals with energy curtailed. That one dealt with the load curtailed, right? So that's why now we have energy in the equation. So again, just to understand the concept, this is our installed capacity. This is the time, the load duration curve over 0 to 100% of the time, which could be a daily, which could be monthly, which could be annual, doesn't matter. And if there is a capacity on outage OK, which may be O1, O2, O3, then you can see that we are not able to supply this much of energy after that capacity outage takes place. So our objective will be to find this E subscript K, and we already know the probability of that happening because we know the probability of this capacity outage, right? So therefore our calculations will become quite simple. If we normalize it by the energy demand, the total energy under the load duration curve, we can find the total energy under this curve. If we normalize it we will get the energy index of unreliability. Usually the EIU is a very small number, 0.000016. It has a string of zeros, whereas its complement, called the energy index of reliability, is actually a string of nines, 0.999999 something. And then the system minutes can also be calculated. It is the energy unsupplied over the peak load. That's the definition, right, of system minutes, which I just now repeated as well. And I'm multiplying it by 60. Why? Because the energy, loss of energy is in megawatt hours, right? So I need to convert it into megawatt minutes. So that's why we get the system minutes by multiplying by 60. So peak load, and this is the risk index in megawatt hours. So although the loss of energy approach has perhaps more physical significance than the loss of load approach, which we saw earlier today, but it has limited applications. We haven't been using it as much. The most popular index, as you have heard me say, is still the LOLE, not the LOEE, yeah? As it happens, because maybe it's simpler to calculate, maybe from a customer perspective, hours per year, days per year is enough, yeah, rather than energy. Not many people understand energy, yeah, but hours per year is easier to interpret, so maybe that's one of the reasons, okay? So we go to our example, yeah, the famous way of learning, and we go back to our same system, 425 megawatt, 1% unavailability generating units with an annual load duration curve between the 100% and the 40% points. So the load, maximum load, system peak load is assumed to be 80. So 80 represents the 100% point, and 80 times 0.4, 32 megawatt will be the lowest load point. And it is a straight line, so that makes our calculations easier. The objective is to determine the EE, energy supplied by each generator, and the risk, loss of energy expectation. So the good thing about this method is that you not only calculate the risk, you also calculate how much energy each generator is supplying. That is a byproduct of the method. So in a way, you are getting more information as opposed to the loss of load expectation method. So let's look at this system data, 25 megawatt, 1% FOR. You know how to calculate the COPT, correct? Now, this information here is not needed for our calculations for now, but I just want to explain a little bit on this. What are the operating costs in any system? Anyone? What are the operating costs? What do they depend upon mainly? Fuel, correct. Operating costs come on fuel, that's why they are variable. You can also call them variable costs. What about the fixed cost? Installation. You pay interest, yeah, or rent, yeah, insurance, and all those things. So they are fixed. They do not depend upon, the one generator being out of service or not producing its full capacity. Nothing. It's constant. Every year you pay the premium, insurance and rental and whatever else. So that's why it's called fixed cost. So if I have these two data, I can actually calculate the total cost of generating that much of energy using the operating cost as well as the fixed cost. And that's very, very useful to the system planner when you can calculate the total cost of production of a certain amount of energy. So we'll not use this for now, but I just wanted to tell you where these numbers are coming from and how we can use them, okay? So in our case, we have a straight line from the 100% to the 40% points, and the peak load is 80. So you can find the equation of the straight line, y is equal to mx plus c, and this is how it turns out to be. Now what is the area under the load duration curve? So if you look at this graph here, yeah, this is the time 0 to 8760. This is the load in megawatt. So the peak load is 80, the lowest load is 32, right? 40%, correct? The load varies from 100% to the 40% points as a straight line, and the peak load is 80 megawatt. So it varies from 80 to 32, correct? So the equation of the straight line, y is equal to minus 0.6x plus 100. We just saw that. So initially, when no generator is loaded in the system, what is the energy curtailed? if no generator is loaded in the system, I'm not supplying any energy, correct? I'm not supplying any energy. That means the total area under this is the energy not supplied, energy curtailed. You can find that. You can find the area under this triangle. You know how to find that. Half of base times the height. And you can find the area under this curve. That's 32 times 8760. And then you can add them up. So you know the total energy required by the load, correct? So the total energy required by the load turns out to be 490560 megawatt hours. So this is our expected energy not supplied before any generator is loaded. So I call it EENS 0, before any generator is loaded. Clear? Now we start to load generators in a priority loading order, economic loading order. Why do we do that? So this goes back to the operating cost. If the fuel for generator A is costing me less, I'm going to load it first. Yeah. If the generator 1 is costing me more, I'm not going to load it first. So that's the reason why I've just shown this data and why I'm loading those generators as A first, followed by B, then C, and then D, because operating D is more expensive and I wouldn't want to, make the costs go higher. So we load the first unit in a loading priority order 1, and once the unit is added, then I have two states. The generator is either out or it's in, correct? So capacity in is 25 or 0. Capacity out is 0 or 25. And we know the probabilities because we know that the forced outage rate of the generators is 1%. So we know the availability is 0.99 and the unavailability is 0.01, correct? So those are the two probabilities. Now energy curtailed, when the generator is out, I'm not supplying any energy, correct? I'm not supplying any energy. So therefore this is the amount of energy curtailed, which is the area under the load curve, correct? But when it is supplying 25 megawatt with a probability of 0.99, how much energy is curtailed? Let's take a look. If it is supplying 25 megawatt, that means I'm supplying this much energy, right? So how much is not supplied? That is this triangle plus this rectangle. You can easily find that area, and that's the number that you see in this particular table. So EK, PK or EI, PI, call it what you will, and then you do that weightage. It's an expectation. We have been dealing with expectations, right? Yeah. So we do that expectation and we sum them up, and this is the energy that is still not supplied after the first generator has been added, correct? So what does it mean? If this was the energy not supplied before the generator was added, and this is the energy not supplied after the generator has been added, so where is the difference coming from? From this generator. So that is why we can calculate the energy supplied by generator A as the difference of those two. So this generator is supplying this much energy. That's an added advantage of this particular technique. We also calculate in the process the energy supplied by each of the generating units. So now we load unit B. We calculate the new probability table, capacity outage probability table. You all know how to do that. We know the probabilities from the capacity outage probability table. We know the capacities CI, we know PI, we only need to know EI, yeah? So we already know for this state, when all the generators are out, when both the generators are out, we already know that we are not supplying any energy, isn't it? That means that we go back to this number, isn't it? And when 25 megawatt is out, we know how much energy is not supplied, is 271560. So you will find that many of the values are coming from that table. So only one new value you need to calculate. What is that value? Capacity out is 0, capacity in is 50. So let's look at that here. Capacity in is 50. So I'm here, right? I'm here on the load duration curve. So how much energy I'm not able to supply? It is this one, right? I can calculate that very easily using that triangle, and how much energy is supplied, obviously the remaining part. So I can put that number in, energy curtailed is this much, EI, PI, and then I add them up, I get this number. So what does this number represent? This is the energy not supplied after the second generator has been added. So the difference between this one and this one will give me the energy supplied by generator B, correct? So that's what I will get. The energy supplied by generator B is the difference between the two values. Okay. Now I add generator 3, yeah, unit number C. We call them A, B, C, D. So we add C. So we have one more capacity in the table. Of course, the probabilities will change according to the capacity outage probability table. And I already know these three values, remember? Those three values are from the previous table. You already know that. Now you need just one additional value. So capacity available is 75. So where are we now? We are here. Capacity available is 75. So we are not able to supply only this little energy here, correct? Which we can calculate as well. So that turns out to be this little value 2281. Again, you do EIPI, and you get this quantity. So after the generator C has been loaded, the energy not supplied is 4,709. And we can calculate the energy supplied by generator C. This quantity minus this quantity will give us the energy supplied by generator C. That's what it is here. Finally, you add the last generator, and this is your new capacity table, and you need one more value. But do you? What is that one more value? 100 megawatt is in, 0 megawatt is out. Yeah. So if you look at that, you are not curtailing any load, right? You are not curtailing any load because your installed capacity is 100 and the peak load is only 80. So therefore, there is no energy curtailed due to that. So it's 0. Yeah. 0. So this is also 0. You can add up the rest and you get this amount. So this is the risk in the system. I have now loaded all the generators in a priority loading order, and I find that the risk in the system is 137.89. Please note that if you do not load the generators in this order, you load them in any other order, the risk will be the same. The risk cannot change. So what will change? The operating costs will change. Fixed costs also no change. The operating cost will change. Therefore, the total cost of producing or generating energy will change. So that's the only other factor, but the risk is known. Once you know the generators, once you know their capacities, their availabilities, the risk is a given. The risk is fixed, okay? So 137 megawatt hours per year, you are not able to supply in this system. Another example, we have a load curve now where there is one straight line and there is another straight line. The peak load is 75 and the lowest load is 30 megawatt, and this is given over 100 hours. Duration can be anything. It can be a day, a month, a week, yeah. And 100 hours is very odd, right? It's not even a week, yeah. 4 days plus, okay. Doesn't matter, as long as you have the necessary data, you can do all the calculations. So consider this load duration curve for a period of 100 hours, the generating unit data given in the table. Assume that the economic loading order of the units is 1, 2, 3. So this is the generation data. We have the first generator which exists in 3 states. So it's a D-rated state unit which we just studied this morning. Yeah, the first thing from yesterday, right? We already know how to calculate the capacity outage probability table for a multi-state generator. Generator 2, the usual 2-state unit. Generator 3, the usual 2-state unit. So the total installed capacity is 25 plus 30 plus 20, yeah, 75, correct? No, 75 is the load. The total installed capacity is total installed capacity is 25 plus 15, 40. So this one is 40 plus 30 plus 20, 90. Yeah. Okay. So the total energy required by the curve, you can calculate, go back to this curve, you can calculate the total energy, right? This triangle plus this rectangle plus this triangle plus this big rectangle. You can calculate the total energy. Quite straightforward. That's why I'm using simple examples where you can verify all the numbers. So that energy turns out to be 4575 megawatt hours. Yeah? When no generator is loaded, the total energy not supplied is 4575. So when you add the first generator, it has got 3 states. It has got 3 states. It's not a 2-state generator, right? That's what we saw, 3 states. So if it is operating at 25 megawatt, the probability is 0.65. If it is operating at a derated state, its probability is 0.3. And if everything is out, the probability is 0.05. Okay? So we'll have 3 states in the calculations. When it is completely out, then this is the energy not supplied. When it is supplying only 15 megawatt, then the energy curtailed is 3075. So we are, I'm not sure if I've shown it in the curve, but you can calculate. When we have only 15 megawatt, we are here, right? So we are not able to supply the rest of the energy, right? Just like in the previous example. So similarly, you can calculate the energy supplied by generator 1 once you calculate this EKPK or EIPI after generator 1 has been loaded. And then you can continue the process, generators 1 and 2 loaded, yeah, and finally with the 3 generators loaded. You find that it is quite a long table because one of the generators is a 3-state unit. That's why it turns out to be quite a long table. So capacity in 75 all the way up to 0, and EI for 75 is 0 because it is just meeting the load demand, yeah. And then all the other cases there is some energy that is not supplied, and the energy not supplied at the end is only 64 megawatt hours for those 100-hour load duration curve. Okay. So this is the summary of the unit energy generated. First generator is generating 2000 megawatt hours, second generator is generating similar amount, third generator is generating only 337 megawatt hours. And the total risk in the system is 64.1 megawatt hours per period. Okay. 2 examples to illustrate to you how we calculate the risk and how we calculate the energy supplied by each generator. Okay. So the expected energy not supplied index 64.08, if you divide it by the energy required, total energy required, which is 4575, we saw that earlier, right? The total energy required is this one, 4575. So if you divide it by that, you will get the energy index of unreliability. And of course, its complement is the energy index of reliability. And then system minutes, you can calculate, you find 51.2. So more than 25, but this is also a very small system, so we can't draw any conclusions from that. For large systems, it will be much larger actually. 51 is still quite reasonable. But the often quoted figure in the literature is 25 system minutes for the system to be very reliable or highly reliable. Okay? So the determination of the expected unit energy outputs is a relatively simple matter in a system without energy limitations. But if the system is energy limited, then you have to consider that in your calculations. And the approach can also consider any number of units, derated capacity levels. We already saw that. One of the generators had derated capacity. And we can also include load forecast uncertainty, just like we did before the break. We did that for LOLE, but no reason why we can't do it for LOEE. It's the same. You have to do the calculations 7 times instead of 1 time. Okay? So the basic requirement is the ability to develop a sequential capacity outage table for the system generating capacity. Every time you add a generator, you have to develop the table. You add one more generator, you have to develop the table again, right? So obviously, if you write a software code for it, it's much easier. Hand calculations will make you repeat the calculations many times over. We can easily do a test for hand calculations, but doing a test on the computer is always harder, right? Yeah. So that's why I think these simple calculations are good. So another exercise for you, 3 non-identical 30 megawatt, 5% forced outage rate generating units and 150 megawatt, 6% forced outage rate unit constitute the installed capacity of a generating system. So it's 3 times 30, 90 plus 50, 140 megawatt. The load duration curve is represented by a straight line between the 100 and 80% over the 100-day period with a peak load of 120. Installed capacity is 140, the peak load is 120. Determine the system risk. Okay, similar to the 2 examples that we have seen just now. I'm sure you can do it, so there is an answer as well. Not sure if you can do it this afternoon because you have some demonstration of software, but hopefully you'll make time later on to check it out. Now there is another exercise here which is actually a very good question from my perspective, because it says a generating system contains 120 megawatt capacity in 6 20 megawatt units which are connected through step-up station transformers. So I think, as they say, a picture is worth 1,000 words. So this picture tells you what it is happening. There are 6 generators. They are all connected through step-up transformers to this generating bus, and then the load is assumed to be connected here. Okay, so that's what the scenario is, which I have described here. The generators have failure rate of 3 failures per year and 97 repairs per year, whereas the transformers have failure rate of 0.1 failures per year and a repair rate of 19.9 repairs per year. Notice the difference between the repair rates of the generators and transformers. You should be convinced, especially those working in the industry, that transformer needs much longer to repair, right? So the repair rate cannot be very high. You can't repair 500 times a transformer in a year. It takes much longer, sometimes weeks, to repair a transformer. Okay? So this is a very practical question. For an annual forecast peak load of 95 megawatt, calculate the risk LOLE, given that the annual daily peak load variation curve is a straight line from 100 to 70%. Calculate the energy index unreliability, EENS, given that the load duration curve varies from 100% to 50%, and the answers are here. So how will you attack this question? How will you deal with this question? I haven't given you any example like this. This is different from the 2 examples. Anyone? Fantastic. These two are in series. We have already done series systems, series parallel, parallel series, mixed parallel, all kinds of combinations. So it's a piece of cake. You know, for 2 series systems, lambda is lambda A plus lambda B. Yeah. Similarly, you can find the mu or the R. So that's how you need to deal with this. And since all the 6 are identical, after you do that, you can use the binomial. Yeah. So therefore, it becomes quite straightforward. Obviously quite long, because I'm asking you to do 2 calculations using 2 different curves, not using the same curve. So it's double the work in a way. But that's what we do as students in order to learn more and more. Okay. So in conclusion, today mostly what we have dealt with, partially yesterday, but mostly today through chapters 7 and 8. We have shown the application of basic probability concepts to generating capacity reliability. We have shown 2 basic indices, the risk indices of loss of load expectation and loss of energy expectation, which is also called as expected energy not supplied or expected unserved energy. You can call it anything. The general notation you should know. This is the energy I'm not able to supply. Very simple. Whereas the loss of load expectation is, this is the number of hours per year that my load is not supplied, right? Or days per year that I'm not able to supply the load. So that's a fundamental difference between the 2. The LOLE technique is still the most widely used probabilistic technique because of its simplicity, perhaps, because there is a reference there, 0.1 days per year. This index has received some criticism because I must have mentioned when I introduced these indices that if the LOLP or LOLE is 1 day per year, for example, you don't know whether you are losing 100 megawatt or 1000 megawatt or 1 megawatt. It does not tell you the severity of the load loss. It only tells you that in the long run, the expected value will be X days per year or X hours per year. Okay, so may or may not have meaning to you. We need to understand that quite clearly. It is, however, possible to produce many additional indices. While we have focused on only 2 indices, LOLE and LOEE, no reason why you can't look at other indices. If you are interested in expected capacity shortage, you can define that as your risk, yeah, and therefore use the capacity outage probability table and calculate the risk of capacity shortfall. Or you can use this expected number of days when specified shortages occur as your risk index. So there are many risk indices you can create for your own system, but the probabilistic way of dealing with them will be the same, just the 2 indices that we have seen. The calculations will be very similar. Expectation, remember, expectation, EI, PI, or PI, PK, TK, or EK, PK, right? Depending upon whether you want energy or you want probability, or if you have capacity, then it could be CI, PI, right? So things like that. It is mainly a question of deciding what indices you want and then proceeding to calculate them. Remember always that the derived values are expected values, long run average values. You don't get to know their probability distribution. That's the disadvantage of the analytical technique. If you really want to know how they are described in terms of a probability distribution, you should go to Monte Carlo simulation. There is no other choice, if that is what is of interest to you. But when we do long-term planning, average value is good enough, right? We don't need to know how the index is described, whether exponential or Gaussian or whatever. The indices should also not be considered as absolute measures of capacity adequacy. So when we find the loss of load expectation, loss of energy expectation, we should realize that they are not 100% expressing the reliability or unreliability of the system, because we have made so many assumptions, correct? You must always not lose track of the assumptions. So they do not describe the frequency and duration. They only tell you days per year or megawatt hours per year. They are not telling you how many times in a year you will have outage, and every time there is an outage, how long will that outage last? Those are the frequency and duration indices. So we are not including those. We are not including operating considerations such as spinning reserve, yeah, dynamic and transient disturbances. I again refer you to the definition of reliability. It has 2 components, adequacy and security. We are dealing with only adequacy here, right? Not security. So therefore, the reliability indices that we are calculating here are not 100% representative of the entire system. They are only representing the static capacity evaluation, not the spinning reserve, not the dynamic nature of the system, not the security aspect. Indices such as LOLE and LOEE are simply indications of static capacity adequacy, which is what I just said, which respond to the basic elements affecting the performance of the system. You can include maintenance, you can include load forecast uncertainty, and still the calculated index will not be 100% representative. So you still need to go back and consider all this if you want it to be holistic. Okay? However, when we do long-term planning, including maintenance and load forecast uncertainty, actually makes the index a little bit more realistic. Yeah, and we can see the variation of the index. We can vary the parameters. We can do sensitivity studies and try to understand where we want to be in the future, how much we want to invest in the future. So there are advantages of what we have learned, but you must remember that we are still not including everything under the operation of the power system for the calculation of these indices. So this still does not make the index an absolute measure. It's a measure of the performance of the generating system, not the absolute measure. Okay? As long as we are aware of that, then I think we are okay. Then we don't need to worry about it. So that concludes this particular chapter. We are slightly ahead of time. But yeah, do you want me to continue, or shall we call it a day and then continue tomorrow? I can't quite complete the next chapter, so sometimes starting the next chapter also has its disadvantages. Go ahead and continue, okay? CH9, please. So we are left with two more chapters. The first one is for interconnected power systems, and the other one is for distribution system reliability. And for distribution system, we'll mostly focus on radial systems, and for interconnected power systems, we'll focus on one particular technique. So let's just sort of introduce this topic today without going into too much detail. So we know by now that we can improve the performance of the system by interconnecting it to another system. I mean, intuitively, we can see that, oh, I have my own system. If I connect it with another system in the hour of need, maybe I can get power from there. Maybe I can get energy from there. And whenever they need, then I can transfer energy to them. I may have mentioned to you on the first day that Singapore has this 2 submarine cables connected to the Malaysian power system. Malaysia is the neighboring state, neighboring country. But as far as I know, we have not received any power from Malaysia to Singapore, but sometimes we do supply power to the other side. Yeah, it depends on the reliabilities of the system, but it actually is there to assist each other, right? Whenever there is a need. Who knows, tomorrow there might be a need, because all the failures are occurring at random. We hope not, and they are undersea cable or lying on the seabed. I don't know how many of you have been to Singapore and or Malaysia, but there are 2 causeways that connect Singapore and Malaysia by land. Yeah, and there is maybe about 3 to 4 kilometer portion where there is a sea. Yeah, so it's lying on that seabed, those 2 500 megawatt cables. So the adequacy of the generating capacity can be improved by interconnecting the system to another power system. Intuitively also we can see that each interconnected system can then operate at a given risk level and with a lower reserve, right? So if I have my own system, I have my own reserve, and I connect my system to another one, and I take some benefit from there, then my reserve can be lower, isn't it? Because I'm taking some additional capacity, correct? So reserve would be lower, and if there is no interconnection, then of course I have to maintain a certain reserve. It will never be lower than that. So the actual interconnection benefits depend upon some of these factors. The installed capacity in each system. I mean, if my system is 10,000 megawatt, and if the neighboring system is only 100 megawatt, I wouldn't expect a lot of support from the neighboring system, is it not? So the installed capacity is quite a factor. The total tie capacity, now tie means the transmission line or the cable between the 2 systems. The capacity of that, it's limited, right? The power capacity cannot be, like I said, 500 megawatts in this case. It could be lower, it could be higher. So the tie capacity is another factor. The forced outage rates of the tie lines. All these cables or transmission lines between the 2 systems, they're going to fail sometime. Even when they're not in operation, they may fail, because sometimes you're just lying there, waiting to fail. And something will happen and you'll fail. So the availability of these tie lines is also a factor. The load levels and their residual uncertainties in each system. So my system is A, the supporting system is B. I have a load level in A, there is a load level in B, right? So these load levels are changing, right? These load levels are not constant. So we need to be aware of the load levels and their uncertainties in each system. So whenever I need power from the neighboring system, maybe they cannot supply because they are on their peak load. Yeah, maybe if they are on their low load, they will be able to supply. So therefore it is dependent upon the peak load in each system. Last but not least, the type of agreement. This is obviously the most important. You have to write down on paper and get it signed by both sides as to when you will support, how much you will support, how much is it going to cost, and things like that, right? So the agreement is very, very important, and I'll share with you some of the agreements that usually these interconnected systems have. So there are several probabilistic methods available which provide a quantitative reliability assessment of interconnected system generating facilities. The LOLE approach is the most widely used, so we are going to continue to use that. There are two basic methods in the literature that can calculate the reliabilities of interconnected power systems. The first one is the probability array method, and the second one is equivalent assisting unit method. Now, as you can see the name probability array, so that means that you create a common probability table which represents system A as well as system B. And from that common table, you can see how much support B can give to A and how much support A can give to B. Yeah, so that's one method. The second method is equivalent assisting unit method. So we will see how much support system B can provide to system A, for example. And we will then model the support from system B as another generating unit, right? We will model the support from system B as another generating unit, and by now we know how to add a generator to our system, right? So we call that equivalent assisting unit method. The assisting unit is modeled as another equivalent generator, and then we treat this together with our system, and then we redo the calculations and we find how the reliability has improved. Obviously, with assistance, the reliability will improve. In other words, the LOLE will reduce, the LOEE will reduce, correct? That's why reliability is improving, unreliability is going down, right? That's what will happen. So in the first approach, a capacity model is developed for each system, and an array of simultaneous capacity outage probabilities is then obtained from the individual models. I'm going to deal with only the second method. Second approach, the assisting system is modeled as an equivalent assisting unit which can be moved through the tie lines. So I'm going to consider how much support system B is able to provide. I'm going to move that support through the connecting transmission line or cable, yeah, model it as a unit and then add it to my system. Yeah, so it's a very interesting method. The evaluation of the risk in the assisted system proceeds much the same way as in an isolated single system study, which we have been exposed to by now, okay? So we'll focus only on this approach, equivalent assisting unit method. Obviously, in a more detailed course, we can look at the first method as well, but we can learn about so many methods. The basic idea is we should know how to do these calculations. And I think the second method is easier to do the calculations by hand. So that's the reason I'm focusing on that. We will also study the impacts of some factors. We will vary the tie line capacity. We will vary the tie line parameters. We will vary the peak loads and the type of agreement between the systems. Yeah, and we'll see how they can impact the reliability and unreliability of the system. So the equivalent assisting unit approach works like this. It represents the benefits of interconnection between the two systems in terms of an equivalent multi-state unit. It could be a two-state unit, but in general, we expect it to be a multi-state unit, which describes the potential ability of one system to accommodate capacity deficiencies in the other. So we'll process assuming that system A is the assisted system and system B is the assisting system. So I'm in system A, you are in system B, you are assisting me. That's what I'm doing now. We can also do the reverse, obviously. Yeah, but once we know one side, we can always do the other side as well, right? The calculation can be repeated very easily. So the capacity assistance level for a particular outage state in system B, because we are going to be assisted by B, isn't it? So we focus on B first. We say, okay, the capacity assistance is given by the minimum of the tie capacity and available system reserve at that outage state. So for example, if the assistance available in system B is 40 megawatt, but your tie line capacity is only 20 megawatt, obviously you cannot transfer more than 20 megawatt, right? So that's what I mean, that even though the system may be able to transport more energy to my system, but because of the constraint imposed by the timeline, I have to consider that as well, right? So we need to consider the constraints imposed by the tie lines. All capacity assistance levels greater than or equal to the tie capacity are replaced by one assistance level which is equal to the tie capacity. So the maximum level of support will be the level of the tie line capacity. That's what it means. And of course there will be other states, but the maximum will be equal to tie line capacity. Maybe the assisting system B is not even able to provide the tie line capacity. So suppose the tie line capacity is 20 megawatt, but system B says, I cannot give you more than 10 megawatt. So that's okay, then there is no constraint from the tie line itself. But otherwise there can be constraint from the tie line as well. So the capacity assistance table, from system B can then be converted into a capacity model of an equivalent multi-state unit. In general it will be multi-state, maybe two-state for simplicity, but in general it will be multi-state. And then we add this unit to our existing capacity model in system A. So as a principle, as a process, this is what it will be. We'll go to system B, we'll see how much support it's going to provide, we'll see how much it can transport through the transmission line or cable, and then we are going to add that model to our own capacity model and recreate the new capacity model, and then use the load model and calculate the new risk. Okay? So that's the process in simplicity. So let's look at an illustrative example. Assume that the two systems A and B are interconnected by a finite capacity tie line and have the data shown in table 9.1. So system A has 5 units of 10 megawatt each and 1 unit of 25 megawatt. So the total installed capacity is 75 megawatt and the daily peak load is 50 megawatt. Okay? System B has 4 generators 10 megawatt each, 1 generator 20 megawatt. So the installed capacity is 60 and its own peak load is 40. So system peak load for B is 40, system peak load for A is 50. They have their own installed capacities, they have their own peak loads. Clear? The tie line connecting system A to B is one tie line, one transmission line or one cable, and the capacity of that line is 10 megawatt and the forced outage rate of that tie line is 0. For simplicity, I'm assuming that the tie line is 100% reliable. We'll see maybe tomorrow when we change the forced outage rate, how it impacts the assisting unit and how our own system reliability gets affected because of that. So these are the data that we have. This is the way the system is. System A, 75 megawatt load, system B, 60 megawatt load, and it can be connected by tie lines. In this case, only one tie line. Okay? So we know how to calculate the capacity model for each system, isn't it? I mean, these are two individual systems. You can calculate the COPT here, you can calculate the COPT in system A. Probabilities less than 10 to the power minus 8 can be neglected, which we have been saying before. So let's look at this. This is the COPT of system A here and the COPT of system B here. Everybody can do that by now, right? So very simple. And these are small systems, so you can do by hand calculations very easily. So the peak load in system A, 50 megawatt. Therefore, the system will fail to meet its own load demand when the capacity on outage is greater than 25, isn't it? The installed capacity is 75, peak load is 50. So whenever we lose more than 25 megawatt, we have loss of load. I mean, we have established that already, right? The definition of loss of load. Capacity on outage may or may not result in loss of load. But if it is more than 25 megawatt, there is definitely a loss of load, correct? So the cumulative probability for a capacity outage of 30 megawatt therefore becomes the LOLE. So what is the risk in system A? The risk in system A is whenever I cannot supply more than 25 megawatt load, right? So if the capacity outage is 30 or more, then this is the cumulative probability, 0.00199,767. Are you with me? Cumulative probability tells us that more than 30 or more than 30 megawatt out, this is the cumulative probability, right? And that's my risk in the system, because up to 25 megawatt I don't lose any load, so I don't need to worry. But anything beyond that, I need to worry. This is the risk. Similarly, what's the risk in system B? The system B capacity is 60 megawatt and the load in system B is, where is that? 40, okay, if you say so. Yeah, peak load is 40. So any outage more than 20 megawatt is going to lead to loss of load in system B. So up to 20 is fine. This state, this is the cumulative probability, 0.00158. So you see that the risk in the two systems is very different, right? Yeah. So system B risk and system A risk. Did I write somewhere? No, I didn't. Yeah, I did. So LOLE index in system A is the cumulative probability for capacity outage of 30 megawatt. Yeah. Similarly, LOLE is the cumulative probability of any capacity outage greater than 20 megawatt. Okay, so we know the numbers there. Now, system B has a reserve of 20 megawatt, correct? Capacity is 60 megawatt, load is 40 megawatt. So its reserve is 20, and this is therefore the maximum assistance it can provide to system A, right? This is the maximum. According to the agreement, maybe the agreement says no more than 10. But so far, I'm not considering any agreements. We just assume that the 20 megawatt is available, okay? So without sharing potential difficulties in system A. The capacity assistance level of system B are obtained from its COPT, yeah? These capacity levels are shown here. So let's go back to system B. System B is going to provide me a maximum of 20 megawatt support, right? So when the system B 60 megawatt is out, cannot provide me any support. 50 out cannot, 40 out cannot, 30 out cannot, 20 out, it's still just able to meet its own load. So it can only provide me support when it is in these two states, correct? So you see here the assistance from, oops, I think the battery is going down. The assistance probability table from system B, if it can provide me 20 megawatt assistance, what's the probability? 0.9039. Yeah, I think this one is also giving up on me. Yeah, here. So system B, if capacity outage is 0, then the individual probability is 0.9039, right? If the capacity outage is 10, then this is the probability, correct? And when the capacity outage is 20, it will not provide me any assistance because it's able to meet its own load. But it can provide me assistance from these two states, right? So 0.90 plus 0.073, that's the probability, 90 plus 0.073. These are the individual probabilities, right? At this probability, it will give me 20 megawatt assistance. At this probability, it will give me 10 megawatt assistance. And 0 megawatt, the rest of the probabilities, isn't it? That means it is meeting its own load. So this is the equivalent assisting probability table from system B, which I'm now going to move through the transmission line. I'm now going to move this through the transmission line, okay? So what do I do? Equivalent assisting model of unit B. So capacity out 0, I can get 0.9 times. Capacity outage 10, I can get 0.073 probability. And capacity outage 20, the probability is very, very low that it will supply me with any support. So the 10 megawatt tie line connecting the two systems constrains the capacity assistance from system B. I can only transfer 10 megawatt, not 20 megawatt. So how do I now modify this table? I can modify this table, the tie line constrained equivalent assisting unit model of system B now. Capacity outage 0 is 0.9039 plus 0.073, isn't it? Because when I'm in this state, I can get 10 megawatt. When I'm in this state, I can get 10 megawatt in my system. So therefore, these two are contributing to the first state. Yeah. And the last one is contributing to capacity outage of 10. Because I can either get 0 or I can get 10, isn't it? So after the tie line, the capacity model that is coming from system B is only a 2-state model. But before that, I have a 3-state model. So that's how the transmission line can actually constrain the support from system B to system A. So once I know this, then it's quite easy. This tie line constrained equivalent assisting unit is now added to the existing capacity model. Yeah, we already know our system A COPT. So you can add the new generator. This is like a generator. This is like a generator, a 10 megawatt generator, which has 2 states, right? So, yeah. Ye wala? Yeah. So we have the support from the system B, which is 20 megawatt available or 0 megawatt out, right? I mean, let's go back here. Assistance of 20 megawatt means from system B 0 megawatt out, correct? Assistance of 10 means 10 megawatt out, right? So I'm now writing it in terms of capacity out. And the 3 probabilities are the same, correct? What I'm saying now is that because the capacity of the tie line is only 10 megawatt, we mentioned that earlier, right? The capacity of the tie line is, what did I say? Let me look at it. Oh, somewhere I must have. Is it here? No, previous one. Yeah, here. The tie line capacity is only 10 megawatt. And of course, it doesn't fail, which is not realistic, but doesn't fail, okay? So even though I have a support of up to 20 megawatt, capacity out 0 means I have 20 available, right? But I cannot get 20 because the tie line is constrained to 10. So when it is in this state, I'm getting only 10. When it is in this state, I'm getting only 10. When it is in this state, I'm not getting anything. Correct? So for these 2 states, I'm getting 10 megawatt. Therefore, the probability is this plus this. That means 0.97. And for the last state, the probability is this. So this is like a 2-state equivalent assisting unit after having passed through the tie line. Okay? So now we can generate the new COPT by adding this new generator of 10 megawatt capacity. So previously, if you go back to the system A COPT, this is the COPT. Yeah, the maximum capacity was 75. Now I have another 10 megawatt. So the maximum capacity becomes 85. And you can recalculate the COPT, right? So that's what is given here, the modified COPT of system A. Okay? So I have capacity outage states and I have individual probabilities. You see here it has almost become 0. That's why I didn't go further. Obviously there's up to 85, right? Because I've added 10 megawatt. But I don't need to. It's almost already 0. Up to 8 digits, it's almost 0 already. Okay? So probability, cumulative probability, and then if you know the load, then you can find out the risk. So the daily peak load in system A is 50, and therefore the loss of load occurs whenever the capacity on outage is more than 35. Previously it was more than? Previously when it was isolated, 25, right? Because the peak load was 50, the installed capacity was 75. So cumulative probability of capacity on outage greater than 25 megawatt would give us the risk. Now we have 35 megawatt reserve. So therefore, the loss of load expectation is 0.00012042. Yeah, 0.0001 more than 35. So it is this state. Yeah, 0.00012042. That is the cumulative probability or the loss of load expectation. So has this improved? Has this improved 0.00012004? 0.00012004 as opposed to the previous one, 0.00199. The lower the better, right? The risk, the lower the better. So the system is more reliable, of course. That's what you would expect intuitively. Now we are quantifying the benefits, okay? So this is how the equivalent assisting unit approach works. And we will get the new LOLE, which is given here, okay? Similarly, if we are interested in calculating the LOLE of system B, when we assist from system A, right now I have shown you that the assistance is coming from B to A. Suppose now I ask you to go back as homework and take the assistance from unit A and then transport it through the tie line to system B and find out the improvement in the risk in system B, then you will be able to do that, okay? So you can just repeat the entire procedure. Now there are several factors that affect the what you call assistance from one system to another, and some of these factors we have already alluded to earlier: the tie line capacity, the tie line availability, the agreements between the systems, the peak loads in the two systems, and so on and so forth. So the factors affecting the emergency assistance we are now going to consider one by one. Do you want me to stop or continue here? Continue? You guys are really driven quite a lot, yeah? So we have now seen that already when we connect the two systems, the reliability improves. We expected that to happen, okay? Now, this assistance depends upon several factors: available capacity and the operating reserve in the other systems, the interconnection limitations, and the type of agreement between systems, right? We can easily appreciate that. The above factors are all interlinked in regard to their impact on the reliability levels. Yeah, so we'll consider them one by one, although they are interlinked. You can also consider them together, but it'll make the analysis more complex. So let's see the individual impacts. We start with the impact of tie line capacity first. So we vary the tie line capacity from 0 to 30 megawatt in steps of 5 megawatt. You remember what was the tie line capacity in the example that we just saw? 10 megawatt. So now I'm saying tie line capacity 0. Obviously no help to system A, correct? If the tie line cannot transmit any power, I'm not getting any assistance from system B. So my original risk, which was 0.00199, stays. And when I have 10 megawatt assistance, this was my new risk, which I saw in the example just now, 0.00012. But what if the tie line capacity is only 5? Then this is the improvement. If it increases to 20, this is the index. Now you see for 25, 30, it is the same. Why? That will tell me whether you are asleep or awake. Why are these two numbers the same? Constrained by the capacity of the assisting system. Assisting system is 60 megawatt, peak load is 40. It will not help me beyond 20 megawatt. So beyond 20 megawatt, nothing will change. You put a 100 megawatt line, tie line capacity, it's not going to matter. It's just a waste, complete waste, okay? So we can do this calculation, and again, you know, if you have the time, please try and do it. A couple of levels, maybe 5 megawatt and maybe 20 megawatt, which is the maximum level of support you can get. So the tie lines considered in the results shown in the previous table, that's this table, 9.7, are considered fully reliable. Remember the tie line forced outage rate was 0? Yeah, I'm assuming that if it is a 5 megawatt line, it's able to transmit 5 megawatt, but normally in practice, that will not be the case. Although you must know that transmission lines are some of the most reliable equipment in power systems. Generators are not as reliable, distribution circuits are not as reliable, but transmission lines are very highly reliable. They are the most reliable components, okay? So it is evident from these results that the risk reduces whenever we increase the interconnection capacity, up to the limit that system B can support system A. Beyond that, there will not be any benefit. So the risk converges to a value which represents the minimum risk that system A can have under these conditions. The risk is getting better and better and better, and it will converge to a value that the maximum capacity relates to. The risk at this limit can be designated as the infinite tie capacity risk. Infinite tie capacity risk. That means regardless of how much you increase the capacity of the tie line, it's not going to increase any further, as there will be no further decrease in risk with the addition of further tie capacity. So it's called infinite tie capacity risk. The infinite tie capacity value is directly related to the maximum assistance available from system B, which in our case is 20 megawatt. Yeah? Hence, increasing the tie capacity beyond 20 will have no benefit to system A. So now, let's change the reliability of the tie line. We assumed until now that the tie line was perfectly reliable. Its unavailability was 0 and its availability was 1. Right, so now we change it. So the tie line availability now, we say consider the case in which there is only one tie line of 10 megawatt as before, connecting systems A and B. Assume that the failure and repair rate of the tie line are 3 failures per year and 1 repair per day. Yeah. So what is the availability? Mu over lambda plus mu. Yeah. Mu is 1, lambda is 3. So you can calculate using this. Lambda is given here, 1 repair per day. So it is 365 repairs per year. So you have to use that number and you will get the availability. Okay, so the tie line unavailability is 1 minus availability, which is this particular number. I think we all can calculate that. So now there are 2 states in the COPT for the tie line, which is the same as before, because it is still a 10 megawatt tie line. So I can only transfer 10 megawatt. Remember, we got the 2-state model before, and that's the model from using this availability. The equivalent assisting unit model for a 100% reliable tie line. If we go back here, for a 100% tie line, reliable tie line is this one, right? 100% reliable tie line is this one, correct? No outages in the tie line. But now we have tie line which may not be available. So how do we modify it? So now the new table is this: tie line capacity, nothing is out. The individual tie line megawatt. These numbers. How did we find these numbers? Unavailability and availability of the tie line is known. So if I want to transmit 10 megawatt, the probability when the tie line is fully reliable is known to me, and the probability when the tie line is not available is known to me. So I can multiply those 2 probabilities and I get this individual probability. Similarly, tie line capacity out 10, the probability is 0.0081. So this is my new transmission line constraint model. I can still get only 10 megawatt assistance when the transmission line is up, and therefore the probability of receiving 10 megawatt is 0.9918 times 0.9777, right? You go back to that table. Unfortunately, it's not on the same page. Yeah, 0.9777. Remember this number, 0.9777. So we multiply 0.9777 with the individual probability of the tie line. Yeah. So that's the new probability, correct? So we can do that, and then we come up with this tie line constraint equivalent assisting unit model from system B. We have considered not only the tie line capacity, we have also considered the tie line reliability. Okay? So this is our new constraint model. If you compare with the previous table, the number was 0.9777, remember? Yeah. Now because it is not 100% reliable, you expect this to be lower, correct? So we are on the right path. We have the new model, and of course now you can repeat the calculation and you will get the new risk. What's the new risk? Again, now I look at 40, cumulative probability of 40 or more, so 0.00013572. This is the new risk. 0.000135. 0.000135. What was the risk before? Oops. Here. Point more than 20, right? No, 10 megawatts, so more than 15. 0.00011972. So you can see that the benefit has changed now when the tie line is not fully reliable. Okay. Okay, we have done this. We have done this. Yeah, so this is the new LOLE. Okay. Correct? Okay, we can also do some more sensitivity studies. We can change one tie line to two tie lines and see how much benefit we derive from there. So now we have a case in which the interconnection between A and B consists of two identical tie lines rated 10 megawatt each. Instead of one tie line of 10, now I've got 10 plus 10, 20 megawatt. The failure rate is still the same. Repair rate is 1 repair per year. Okay, so the COPT for the two tie line interconnection is shown here. Yeah, so it can exist in 3 states. Either both of the tie lines are operating, so this is the probability. You know how to calculate that, right? COPT for 2 lines, it's like using binomial distribution. A plus U square is equal to A square plus 2AU plus U square. So this is A square, this is U square, this is 2AU, yeah, where A and U can be calculated from these numbers, right? Correct? Yeah, so this is what you get anyway. Hopefully you can verify those numbers. So the effects of the tie line constraint is included by combining the capacity outage states of both the equivalent assisting unit from system B and the tie lines. Yeah, so again, the process is the same. You have a different model. This is the model of the tie line now. We can actually get 20 megawatt over from system B. Previously, we were able to transport only 10 megawatt, but now we are able to transfer up to 20 megawatt. So this is the tie line capacity model, but we also have the model from system B. So the system B model has to go through the tie line model, and then you have to get a new model of the tie line constrained capacity outage probability table, correct? So that's what we do next. The tie line constrained equivalent assisting unit model of system B is given in a table, but we'll add it to the table of system A. The new installed capacity in system A now is 95, isn't it? Because we can get 20 megawatt support from B. The loss of load results for a capacity outage greater than 45 megawatt now. It was 35 megawatt before. In the isolated system, it was 25 megawatt, right? With the 10 megawatt line, 35. 20 megawatt line, 45. The modified COPT is also shown for you. The cumulative probability of the first load loss event greater than 45. So that happens to be 50. That will give you the loss of load expectation in system A. Okay? And that turns out to be 0.405290. As expected, the reliability has improved significantly. Previously, it was only 0.30 something. Now it is 0.40. The lower, the better. Correct? So those calculations are shown here. I'm just going to show you this table, and we're going to stop here. So the capacity outage states from equivalent assisting unit, and this is the tie capacity states. So if you go across, these are the states from system B. If you go across, these are the states from system B. If you go in terms of the row, these are the states from the tie line. And I need to put the two together, right? So for example, if the capacity out from from system B is 0 and the capacity out from tie line is also 0, then I get this probability. How do I get that probability? How do I get that probability? Yes? Remember, independent events, probability of A and B is probability of A multiplied by probability of B. So you know the capacity out 0 megawatt from system B. You know capacity out 0 megawatt from the tie line. You multiply the two and you will get this probability. Okay? And then you see there are different states. 10 megawatt out, 0 megawatt out from here, but 10 megawatt out from the line. So total will be 10 megawatt out. 10 megawatt out here, 10 megawatt out from the line, total will be 20 megawatt out. So you have different states and you can come up with this capacity outage probability table, passing the available table from system B through the tie line model, yeah, and combining all the common states. So there are more than 2 states with 10 megawatt out. So you see here, 10 megawatt out from the system B and 10 megawatt out from the tie line. 10 megawatt out from system B, 10 megawatt out from the tie line. You can only transmit 10 megawatt, is it not? Yeah, because tie line is 20, correct? And then if tie line is 20 megawatt out, you can't transmit anything, correct? So that's why you have to combine some of these states which are similar and then get this particular table. We have done this in a previous example yesterday, so it shouldn't be too hard. Okay, and then we obtain the modified COPT, and then the cumulative probability of 50 or more out is this one, 0.405290. That's the risk in the system, the new risk in the system. Clear? Okay. So compare this value with the original index obtained for 20 megawatt of fully reliable tie capacity. We can see that the inclusion of the tie line availability results in an increase in the risk expected. We are quantifying the increase. We expect that the risk will increase surely. So such an increase is only marginal since the tie line availability is unavailability is usually very small. As I mentioned, tie lines are fairly reliable. Okay. So we have seen the impacts of tie line. We have seen the impact of tie line capacity. We have seen the impact of tie line forced outage rates. Now the only thing that I want to talk about is multi-connected systems, and we'll probably complete this tomorrow, okay, in addition to the distribution systems. All right. Thank you very much again. You have a nice day and do prepare for the test tomorrow.
Machine lab, electrical department. So